Welcome to ECE 761 Robotics Lecture number 13, Jacobians and Cartesian Control. Now, Jacobians are a matrix that relate tip forces to joint torques. They also convert from Cartesian coordinates, x, y, z, into joint motion. For example, if the relationship between the tip position and the joint angles is as follows, then the derivative of p is the partial respective spected theta 1 times theta 1 dot plus the partial of f with respect to theta 2 times theta 2 dot, and so on. This is called the Jacobian. Again, it relates joint velocities to tip velocities. For example, if I know the joint velocities, I can tell you how fast the tip is moving, or by inverting the Jacobian, if I know the tip velocity, I can tell you what the joint velocities are. For example, the RR robot we've been using, x versus y, the tip position is function theta 1, theta 2. The Jacobian then is minus sine theta 1 minus sine theta 1 plus theta 2 minus sine theta 1, 2, and likewise cosines. What that means is that if I have a given point and its joint angles, if I know the joint velocities, I tell the tip velocity. So here's how the robot is moving in joint angles. This is how the tip is moving. Or, going the other way around, if this is the tip velocity, that's the joint velocities. So that's where Jacobians are useful. It converts from tip positions, usually what we care about, to the joint velocities, stuff the robot cares about. With Jacobians, instead of using feedback control in joint angles, I can use feedback control in Cartesian coordinates, x, y coordinates. And to do that, I've got my robot. Input is torque, output is angle. Or velocity. Joint velocities get converted to tip velocities through the Jacobian, and we're going to get tip position. Something we'll cover tomorrow. Torque is related to force by the Jacobian transpose. And Jacobians are pretty useful. They keep on appearing. If I calculate the error in the position, that gives me a force. To convert to a torque, multiply by Jacobian transpose. So at this point, I have Cartesian control, x, y. I have Cartesian control right here, force in the x and y direction. At this point, the Jacobian converts you to robot coordinates, then back to Earth coordinates. To do this, however, you've got to keep away from singularities. If the Jacobian is ever 0, then I've got a problem. The Jacobian is 0 at the extremities for our robot, and also right at the origin. So I've got to keep away from those two spots. So, with the Jacobian, I can now implement Cartesian control. That's basically this. I want to specify the path I want to follow. It's going to be a square in Cartesian coordinates. I'll then control the tip position, meaning through the Jacobian the torques, to force the tip to follow. The first step is to define the tip position versus time. You're going to use cosine interpolation. So this is x and y coordinate. I can then tell you the tip position using a PD controller. So it's going to be the Jacobian transpose times your PD. And here to put the poles at minus 10 plus minus j10, kind of an arbitrary spot. P is 200, D is 10. To simulate that, this is similar to what your homework is going to be. It's pick a shape other than a square and repeat what we're doing here. First, I wanted to use path planning to find the points of a square, do a spline curve fit, every second go from point A to point B. Once I know the tip positions, I know the velocities and accelerations. Here's the control law. Given the tip position, I know the joint angles. The j equals 1 to 10 just lets me make the integration step size 10 times smaller. Gives better numerical properties. At any given point, I know the tip position, I know the Jacobian, The velocity is Jacobian times joint velocities by feedback control law. Here I just used the PD control law of 16 and 6, again kind of arbitrary, where we want to put the poles. This shows off a little bit better because lower gains give you more error, and I can see what's happening. And then once I know the torque is Jacobian transposed times your PID gains. And these other terms will be adding in one at a time. So what I have right now is just a PD control law, and notice that the PD control law is in Cartesian coordinates, XY coordinates. And I'm sort of tracking. This is similar to what we did in the previous homework set, but now in XY coordinates. The reason it's not tracking is because I've got gravity terms, I've got velocity, I've got acceleration terms not taken into account. If I do that, I miss. So this is the desired joint angles and actual angles, and the torques that I'm applying. To do better, let's compensate for gravity. I know the tip position, meaning I know the joint angles. I can pre-calculate the force due to gravity. If I add that in, it's no longer falling below. That's the gravity compensation. It's still lagging behind. The lagging behind is just property of PD control laws. I'm just feeding back the error in position. So I have to have an error for it to follow. But the gravity compensation helped quite a bit. Like we did before, I can do better. If I do some feed forward terms, let's feed the desired velocity versus the actual velocity. Throw that term in. This is a feed forward term. I pre-calculate the desired velocity. That tells what the force PID is, which tells me what the torques are. I'm pre-applying torques based upon the desired path. By having that feed forward term, I have much better tracking. But now I'm overshooting. The reason is when I start out, I'm accelerating going up. Now I'm decelerating. And the actual robot, the blue line, overshoots due to the inertia of the robot. That too I can compensate for. I know the desired position. I know the desired velocity. I know the desired acceleration. If I add that in as a feed forward term, I now have almost perfect tracking. So here we have XY control of a robot with almost perfect tracking. To use XY coordinates, I have to use Jacobians, and I use them a couple places. I have the Jacobian transpose, converting forces to torques. I have the Jacobian, converting joint velocities to tip velocities. That's one use of Jacobians. It lets you convert from angles to XY position and use something that makes more sense to people, the tip position. And here's the tracking on the top curve and the resulting torques. The homework for homework number 13 is to repeat what we did here in the lecture, but instead of tracing out a square, pick a different shape. You pick what it is. Star, Batman symbol, whatever you like. That's lecture number 13 for robotics.